So, we will continue our discussion on IC engine, and today we will discuss about diesel cycle. In the last lecture we have discussed about the mathematical analysis of Otto cycle, and we have quantified the thermodynamic efficiency of Otto cycle. So, just today before I go to discuss about the diesel cycle, I will recapitulate the Otto cycle once again. If you can recall that Otto cycle basically in a 4-stroke engine SI engine is approximated by an air standard cycle, and this ideal cycle is known as Otto cycle. While you are talking about Otto cycle, and if you can recall the PV and TS diagram, and just I will try to recapitulate Otto cycle, and if we try to recall the PV and TS diagram. So, this is P and this is V diagram, pressure P versus V diagram, and then corresponding TS diagram. So, we have seen that we have taken a few approximations like that whenever air is introduced, not air, rather air fuel mixture is introduced in the engine cylinder during intake stroke, we have assumed that the entire process is occurring at a constant pressure. So, we have approximated this is a constant pressure intake, air fuel mixture, that is charge is being introduced into the cylinder at constant pressure. This assumptions is not very bad assumptions, rather this is a good approximation, because pressure inside the cylinder should be slightly less than atmospheric pressure, otherwise there will be a frictional loss through the intake manifold while air fuel mixture is flowing through the intake manifold to the cylinder. Similarly, we have assumed that whenever after the end of the intake stroke, that is air fuel mixture is being introduced, then all the valves will be closed, exhaust valve is remaining closed from during intake stroke as well, and during the compression stroke it will remain closed. And what we are doing, we are closing the intake valve as well at the beginning of the compression stroke. So, we have approximated compression stroke by an isentropic process. So, if this is intake stroke, then we are approximated that the compression stroke is represented by an isentropic process. Then what will happen at the end of the compression stroke? We should ignite, rather we should switch on the spark plug. So, the combustion will take place, and the combustion is represented by constant volume heat addition process. So, in case of Otto cycle, the combustion process is represented by a constant volume heat addition process. Then after the end of the combustion, we will have high temperature, since it is a constant volume process. So, pressure will increase as a result of the increment of the temperature inside the combustion chamber, inside the cylinder. So, we will have a rise in pressure, and that will create a thrust on the piston face, and it will allow piston to go back from TDC to VDC, and we will have a power stroke, that is expansion stroke. Again, we have approximated that power stroke by an isentropic process, and then finally you are having constant volume heat rejection, that is exhaust blowdown. I mean, whenever piston is reaching towards the VDC at the end of the power stroke, we open exhaust valve. We have discussed about the reason behind opening the exhaust valve slightly below VDC at the end of the power stroke. That means we should close the exhaust valve whenever piston is far away from VDC towards the end of the power stroke. We have discussed about the reason, because why we are doing so, because we need to expel out combustion product before piston reaches at VDC at the end of the power stroke. This will allow some enthalpy to go away, that is fine, but what it will do, it will weaken the pressure inside the cylinder, so that in the next stroke, when piston is coming from VDC to TDC, that is exhaust stroke, then piston will create less resistance while it is traversing from VDC to TDC. Since I told you that out of this 4 stroke we are having only 1 power stroke, and there are 3 ideal strokes, so it is quite good practice that we should open exhaust valve before piston reaching at VDC at the end of the power stroke, so that the piston will face less resistance, and we require less power, which for the movement of the piston from VDC to TDC. So, these 4 processes are the intake, compression, power stroke, and blowdown. So, the combustion process is represented by constant volume heat addition Q in, and then exhaust blow down where, because whenever we are opening the exhaust valve, some amount of combustion product will go away, will expel out from the cylinder, and it will carry enthalpy from the cylinder. So it is it is exhaust blow down, so it is Q out. So this process is constant volume. My question today is, whatever approximation we have taken, that isentropic process, compression process is represented by isentropic process, expansion process is represented by isentropic process, while constant heat addition, that is combustion process, and exhaust blow down, heat output. So heat rejection. So heat addition and heat rejection, both these processes are approximated by a constant volume process. Constant volume heat addition, constant volume heat rejection. As I said you that intake process is a constant pressure process. This is not a very bad assumption, because pressure is remaining fairly constant while we are introducing air fuel mixture into the cylinder, and pressure should be slightly less than atmospheric pressure only to account the frictional losses in the intake manifold. Similarly, when we are having compression process, the isentropic process, we are approximating by an isentropic process. This is also not a very bad assumption, because see, this is a good approximation, except at the beginning of the compression stroke, where intake valve is still open. As I have discussed it again, that exhaust valve is remaining open even at the end of the even at the beginning of the compression stroke, because during intake stroke we cannot completely remove all the residue from the cylinder during the exhaust stroke. So some amount of air fuel mixture will be will mix with the residue of the combustion product, and for that we need to keep open the intake valve, or even when piston start traveling from BDC towards TDC at the beginning of the compression stroke, only to have a better efficiency. So only to have efficient combustion. So at the beginning of the compression stroke, since the exhaust intake valve is remaining open, so and at the end of the compression stroke we are switching on the spark plug. So except these two cases, at the beginning and at the end of the compression stroke, the process is the isentropic, that whatever we have assumed, this is a good approximation. Similarly, when we are approximating the combustion process by a constant volume heat addition, this is also not a very bad assumption. This is also good approximation, because normally what is done when piston is below TDC, at the end of the compression stroke, spark plug switch is on, and whenever piston is reaching at the TDC at the end of the compression stroke, because switching on the spark plug you require a finite amount of time, although it is of the order of microsecond, but still we require a finite amount of time, and by that time if we start switching on the spark plug when piston is slightly away from the TDC, rather slightly below TDC, and if we switch on the spark plug, by the time when piston reaches at TDC, that spark plug switch is on and entire combustion is completed, and as if the volume is remaining constant. So constant volume heat addition is not again a bad approximation or bad assumption, so it is also a good approximation. Third thing is expansion, power stroke. It is again represented by an isentropic process, but again this is also good approximation, except two cases. One is, see, at the end of the compression, at the end of the power stroke, when we open the exhaust valve only to have a blow down. So and at the end of the power stroke, rather expansion stroke, we open the exhaust valve only to have a blow down, only to reduce the resistance, only to reduce the pressure into the cylinder, so that the piston will face less resistance while coming from BDC to TDC again during the exhaust stroke. And second thing is that beginning of the power stroke is also affected by the last part of the combustion product. Beginning of the power stroke is affected by the last part of the combustion process. So except end of the power stroke, rather end of the expansion stroke or power stroke is affected by the opening of the exhaust valve, while beginning of the power stroke is affected by the last part of the combustion process. So except these two things, the process is isentropic, that whatever we have assumed, this is also a good approximation. Last one is again exhaust blow down. So whatever we have assumed, that before piston reaches at BDC during the power stroke, we open exhaust valve only to have a blow down, only to expel out some combustion product from the cylinder, and this is whenever piston is reaching at BDC, whenever piston is reaching at BDC, then we start intake valve is remaining closed or exhaust valve is remaining open. Whenever piston is reaching at BDC, as if and piston is traversing from BDC to TDC, and that is constant pressure. So whatever I am telling that blow down in real engine therefore must not be constant volume, not quite rather constant volume process, because there is no high pressure in the cylinder to resist piston in the flowing exhaust stroke. So what we are doing only to reduce the pressure inside the cylinder, so that the piston while traversing from BDC to TDC at the exhaust during exhaust stroke should not experience huge resistance, and to take into account that what we are doing, we are opening the exhaust valve when piston is slightly away from BDC during the end of the power stroke, and we are approximating the volume is remaining almost constant because piston is slightly away from BDC. So volume is remaining almost constant. So the heat rejection, that is exhaust blow down, it is also a constant volume process, and this approximation is not a very bad approximation. So we have discussed about the 4 different process, because we have taken approximation while doing some mathematical analysis only to have a quantification of thermodynamic efficiency of the Otto cycle. And today we have discussed about that the whatever assumptions, whatever approximations we have taken, those approximations are not bad approximations, rather these are good approximations, except a few cases that we have discussed, that at the beginning of the compression stroke, at the end of the compression stroke, at the beginning of the power stroke, and at the end of the power stroke, I have discussed. And that if I draw the TS diagram, so this process is isentropic process. So if I give the name, say this is 1, 2, 3, 4. So 1, 2 is the 1, 2 is isentropic compression. Then 2 to 3 is basically combustion process, that is heat addition process. So peak pressure and peak temperature will go high, because the constant volume process, temperature will go high because of the combustion. Since process is volume is remaining constant, so pressure will go high. So 2 to 3, 3 is the peak temperature, T3 and P3 are the peak, P3 is the peak pressure and T3 is the peak temperature. Similarly 3 to 4 is again isentropic process, isentropic expansions, and 4 to 1 is the blow down, that is heat, this is the heat rejection, Q out, and this is Q in. So we have discussed that, last class we have discussed about the thermodynamic analysis of the Otto cycle. We have calculated the thermodynamic efficiency of the Otto cycle considering air to be an ideal gas, and we have used ideal gas relationship, and we have taken a few approximations. Today we have discussed that the approximation that we have considered only to drive the mathematical thermodynamic efficiency or thermal efficiency of the Otto cycle, those approximations are not very bad approximations, rather those are good approximations except a few things, and that is what we have discussed. So today we will discuss about, with this complete the discussion about the Otto cycle, and we will again discuss about we will work out a few examples based on the Otto cycle, but now we will discuss about the diesel cycle. This is very important. So today I will discuss about diesel cycle, and we will try to quantify the thermodynamic efficiency. Before let me discuss you that since the constant combustion process is represented by a constant volume process, also the exhaust blow down, that is heat rejection, is represented by a constant volume process. Otto cycle is sometimes known as constant volume cycle. So Otto cycle is sometimes known as the constant volume cycle, because we have approximated that, and this is not a very bad approximation, that the combustion is that the heat addition process is a constant volume process. So today now we will discuss about the diesel cycle, that 4-stroke engine CI, 4-stroke CI engine, 4-stroke cycle CI engine, again we are approximating by a air standard cycle, and the ideal cycle is known as diesel cycle. While we are trying to analyze the thermodynamic, a change of the thermodynamic state at the end of each and every strokes during the of a 4-stroke cycle CI engine, we are approximating by air standard cycle, and the ideal cycle is known as diesel cycle. Instead of having constant volume combustion in a diesel cycle, we are approximating the constant pressure. Because why we are doing so, let me discuss first this, and then we will go to drive the mathematical analysis, or rather towards the quantification of thermodynamic efficiency or the thermal efficiency of the diesel cycle. In a CI engine, if we try to recall that while we have discussed about the difference between SI and CI engine, we have discussed that in a CI engine, combustion process is not similar to what is there in a SI engine, because in a SI engine we normally introduce during the intake stroke air fuel mixture, there is charge, but in case of a CI engine we introduce air through the intake manifold during the intake stroke. We compressed air to a temperature and pressure, and that at the end of the compression stroke, when the temperature and pressure of the air is high, then we we spray fuel through a fuel injector, and we utilize the high pressure temperature condition to ignite to initiate the combustion itself. Now question is, whenever we are introducing fuel, when you are spraying fuel into the cylinder at the end of the compression stroke through fuel injector, we require finite time, and we will discuss while we will be discussing about the combustion process that it is known as ignition delay. That means we require finite time to inject, to supply fuel into the cylinder. Whenever you are supplying fuel in a spraying fuel into the cylinder in a spray pattern, in a nice spray pattern, because it is required, that again we will discuss, we require finite time and only to supply fuel, only to spray fuel through fuel injector, because fuel injector is also a mechanical device. It requires a finite time to to create a spray pattern to supply fuel into the cylinder. Also this is known as physical delay, and also the moment at which we supply fuel, because fine, we should try to fragment the fuel particle into more finer and finer droplet, but still we require some chemical delay, because the moment at which we supply fuel, it won't take part in the combustion, it requires a certain amount of time, although it is of the order of millisecond, but we require finite time. So these two, and it depends upon the chemical characteristics of the fuel. So this physical delay together with the chemical delay is known as ignition delay. Considering this ignition delay, we are approximating that the pressure inside the cylinder will remain constant while entire combustion is completed. So why? Because we cannot represent the combustion process by a constant volume process. As I said you that the movement of the piston is very instantaneous. So it's very is rather spontaneous. Movement of the piston is very spontaneous. So whenever piston is reaching at the whenever piston is reaching at TDC at the end of the compression stroke, it is not possible to keep piston hold for a while over there, so that the volume will remain constant and entire combustion will be completed. Instead, what is done normally, rather to explain this, we can explain it in this way, that whenever piston is slightly below TDC at the end of the compression stroke, we try to supply fuel through fuel injector, and as I said you that we require some amount of time accounting the ignition delay, which is nothing but the physical delay plus chemical delay. So that delay period, I mean, we will considering the delay period whenever piston is slightly below TDC and we start spraying fuel, and maybe combustion might start, and then again when piston is coming after reaching TDC, and when again piston is traveling back from TDC towards VDC during the next stroke, that is expansion stroke, combustion may be lasted. So and during that we cannot assume that the volume will remain constant. That means we have started spraying fuel when piston is slightly away from TDC during the end of the compression stroke, and combustion may be initiated over there, but combustion will last even when piston is returning back from TDC towards VDC during the beginning of the power stroke. So while it is happening, we cannot assume that the volume will remain constant, rather we can assume the pressure inside the cylinder will remain constant. That means to take into account the effect of ignition delay, and we are approximating that the combustion will start when piston is slightly away from TDC, and it will last when piston is returning back again from TDC, and rather while slightly away from TDC during the beginning of the power stroke. And during that process, volume will no longer remain constant, rather pressure will remain constant, that we are approximating, and that is why combustion process in a diesel engine is approximated by a constant pressure process, and sometimes diesel cycle is known as constant pressure cycle. So diesel cycle is known as sometimes constant pressure cycle. So today we will discuss about the again we will discuss about the thermodynamic, we will do the thermodynamic analysis of the diesel cycle, and we will discuss, we will try to quantify the thermodynamic efficiency of the diesel cycle. Fine. So again we have to draw PV and TS diagram. So if we draw the PV and TS diagram, so this is P, this is V, and this is temperature entropy diagram TS. So intake process, only air is being introduced during the intake stroke, and again we are approximating that the pressure will remain constant. Again I am telling that the pressure inside the cylinder will be slightly below the atmospheric pressure, and this approximation is not a very bad approximation, rather this is a good approximation, and we are approximating this, the process will be like this. So maybe, and P naught, this P naught will be slightly less than atmospheric pressure, only to take into account the frictional losses in the rather frictional losses in the intake manifold. Then what is done, then while the cylinder is filled up with the air, fresh air, then we are having compression stroke. So compression stroke again is represented by an isentropic process, and that is what we have discussed. This is also not a very bad approximation, this is also good approximations. The intake valve will remain closed or remain open at the beginning of the compression stroke, and at the end of the compression stroke again we have to ignite some amount of, we have to spray some amount of fuel, a required amount of fuel to initiate combustion. So during these two things, during these two cases, at the beginning of the compression stroke and at the end of the compression strokes, the process is an isentropic process, and this approximation is a good approximation. So here we are having isentropic process, maybe this process is so fine, isentropic compression stroke. So maybe 1 and 2, and then in a SI engine we have approximated this is a constant volume process, but here it is a constant pressure process. That is, combustion process is a constant pressure process. That is what we have discussed a little ago, that instead of considering a volume will remain constant, we can assume the pressure will remain constant, because it will start when slightly below when piston is slightly below TDC, and it will last even when slightly coming from TDC towards BDC. So we are approximating, instead of volume to be constant, pressure will be constant pressure, and then again power stroke is approximated by a constant rather an isentropic process, again by an isentropic process, and finally exhaust blowdown is again approximated. So this is 3, this is 4, this is 5, and let us say this is 6, this is 6. So 4 to 1 is exhaust blowdown. That means this is similar to what we have discussed in the context of discussion of SI engine. So we have seen that the only difference is that here combustion process is represented by a constant pressure, and that is why this cycle is sometimes known as constant pressure cycle. So this is the heat addition, Q in, and this is exhaust blowdown, that is Q out. And this is not a very, this is also good approximation, because we should open exhaust valve when piston is a little away from BDC during end of the power stroke, and we will need to expel out certain amount of combustion product only to reduce the pressure inside the cylinder, so that the piston will face less resistance while traversing back from BDC to TDC in the next stroke, that is exhaust stroke. So this is the PV diagram. Now if we draw the TS diagram, then again we will get that 1 to 2. Here pressure at the end of the compression, temperature at the end of the compression should be high enough as compared to the SI engine, because we are utilizing the high pressure and temperature of the air to ignite the fuel itself, because we are utilizing the self ignition properties of the fuel itself without having an external agent like spark plug in case of a CI engine. So the temperature and pressure P2 and P3 remain same the peak pressure, because we have approximated this process, the combustion process, by a constant pressure process. Rather T2, T2, and then of course, so T2 will be high, that is at the end of the compression process temperature will be high. Then we are having combustion process, so 3 will be again higher than the temperature 2, T3 will be higher than temperature T2, and then we are having 3 to 4, that is exhaust blowdown, and then we are having 3 to 4, 4 to 1 and 2 to 3, and 4 to 1 is the exhaust blow down. So, this is Q in heat addition, this is Q out heat rejection. So, 1 to 2 and 3 to 4, these processes are approximated by an isentropic process, and these are not very bad assumptions that we have discussed. Fine. Again, while we are trying to do the analysis, thermodynamic analysis, we have to, because as I said you that the 4-stroke cycle CI engine is approximated by air standard cycle, and the ideal cycle is known as diesel cycle, while combustion process is represented by constant pressure process, and sometimes it is known as constant pressure cycle. So, we will be using treating air to be an ideal gas, and we will be using ideal gas relationship to drive the thermodynamic efficiency or the thermal efficiency of the diesel cycle. So, now we will write different processes. So, process 1 to 2 is very important, the other process 6 to 1 is very important. So, I will write process 6 to 1, that is known as constant pressure intake. So, this is known as constant pressure intake. Pressure is remaining constant, that is P naught, and here what is done, intake valve is open and exhaust valve is closed. So, what will be work done, because it is a constant pressure intake, volume is changing. So, work done W 6 to 1 will be equal to P naught into V1 minus V6. V1 is VDC and V6 is VTDC. Rather, that is, this is not 0.6. So, this is VTDC and this is VVDC. So, V1 minus V6. So, work done during the intake stroke is like this. Next, we will move to another process. So, process 1 to 2. So, if I write process 1 to 2, so process 1 to 2. What is this process? Compression, isentropic compression. Again, we are telling that I have written the ideal gas relationship in my last lecture. We will be utilizing those, while again we are try to drive the thermodynamic efficiency or thermal efficiency of the diesel cycle. So, isentropic compression strokes, we will write that all valves are closed. All valves are closed. That is, intake and exhaust valves are closed. So, although at the beginning of the compression stroke is affected by the opening of the inlet valve, and towards the end because of the spraying of the fuel. So, but we are assuming that all valves are closed. So, if that is the case, so isentropic process, there should not be any heat interaction, right. So, Q1 to 2 will be equal to 0, W1 to 2 we have to calculate, W1 to 2 will be, if we go back to PV diagram, P2 V2 minus P1 V1 divided by 1 minus K, that equal to R into T2 minus T1 divided by 1 minus K, that equal to U1 minus U2, that equal to CV into T1 minus T2, CV into T1 minus T2. These are all we can obtain from ideal gas relationship, very straightforward. So, what will be temperature at the end of the compression stroke? T2 will be equal to T1 into V1 by V2 to the power K minus 1 is equal to P2 by V2 by V1 to the power, sorry, V1 by V2 to the power K, that equal to P into RC to the power K, where RC is equal to compression ratio is equal to VVDC by VTDC is equal to V1 by V2. If we go back to my previous slide, V1 and V2 are nothing but the VVDC and VTDC, fine. So, this is the compression ratio. So, we have obtained no heat interaction, isentropic process, work done we have calculated during the process, during the compression process, because you need to do some work, and that is for energy you are getting from the flywheel. temperature at the end of the compression process is T2 like this, and similarly pressure at the end of the compression process P2, P2, that equal to P1 into V1 by V2 to the power k, that equal to P1 into V1 by V2 to the power k is equal to P1 into RC to the power k, where RC is equal to compression ratio, that is what we have discussed. That is what is discussed. And T2 is equal to T1 into V1 by V2 to the power k minus 1 is equal to T1 into V1 by V2 to the power k minus 1 is equal to T1 into RC to the power k minus 1, where RC is equal to compression ratio. Fine. So, process 1 to 2 we have identified the change of pressure and temperature at the end of the compression stroke that we have calculated using an ideal gas relationship. So, now we go to process 2 to 3. This is very important. Process 2 to 3 is a combustion process. This is combustion process. Rather, we have assumed that this is represented by constant pressure heat input or heat addition process. Both valves are closed. Both valves are closed. Process 2 to 3 is a combustion process, constant pressure heat input or addition, both valves are closed. So, here pressure is remaining constant. So, what will be work done at Q 2 3. So, Q 2 to 3 specific and heat addition is equal to what? Pressure Cp into T3 minus T2. Cp into T3 minus T2, that equal to H3 minus H2, change in enthalpy between point 3 and 2, and W223, this is very important, that is Q223 minus U3 minus U2, that equal to P2 into V3 minus V2. Pressure is remaining constant, change in volume V3 minus V2, right? V3 V2 again, if we go back to my previous slide, V3 and change in volume, there is a change in volume during the combustion process, that is volume is no longer remaining constant, that is what we have discussed, that it will combustion will start when piston is slightly below TDC, it will last even when piston is coming back from TDC, so that the volume will change, volume will no longer remain constant, rather we are approximating pressure will constant, and this is a very good approximation. So, from this expression of work done we can see that the we can have work done, and W23 will be Q23 minus U3 minus U2 is equal to P2 into V3 minus V3, and T3 is equal to T max, and this is the maximum temperature. So, that is very important. Now, this is what we need to this is what will be required while we are while we try to obtain the thermodynamic efficiency or the thermal efficiency. Fine. Here see, during the combustion process, rather Q2 to 3, I can write that Q2 to 3 will be equal to how much? Mass flow rate of fuel, calorific value of the fuel, and combustion efficiency, that equal to m dot m mass flow rate of mixture into Cp into T3 minus T2. So, this is mass flow rate of mixture, that is mass flow rate of air plus mass flow rate of fuel into Cp into T3 minus T2. So, this is the heat addition in the combustion process. This is heat addition in the combustion product. Mass flow rate, what is the amount of heat is being added in the combustion process. So, mass flow rate of air plus mass flow rate of mixed fuel into Cp into T3 minus T2, and that will be equal to mass flow rate of fuel into calorific value of the fuel itself is equal to combustion efficiency. Fine. What we have seen that at the during the combustion process, volume is changing from V2 to V3, right. So, since volume is changing, one ratio is defined here which is known as cut-off ratio. So, cut-off ratio, which is very important and is defined, cut-off ratio, it is beta is equal to V3 minus V3 by V2, that is V3 by V2, that is small V3 by V2 is equal to T3 by T2. So, this is defined as the ratio of change in volume, it is defined as the change in volume that occurs during combustions, that that occurs during combustion. So, in a combustion process, during the combustion process, volume is changed from V3 to V2. This ratio of V3 by V2 is known as cut-off ratio, and I mean as defined and indicated by defined by beta. So, next process is 2 to 3 we have identified, and next process is what? That is 3 to 4, that is again isentropic. Process 3 to 4, this is very important, that is known as isentropic expansion process, and that we need to know. So, process 3 to 4. So, this is again isentropic expansion, or sometimes it is known as power stroke. All valves are closed, rather both valves are closed, both valves are closed. We are considering, but again I will say that whenever piston is reaching at BDC, rather before reaching piston BDC, we open the exhaust valve only to have exhaust blow down, only to reduce pressure inside the cylinder, so that the piston will face less resistance during while coming from BDC to TDC at the end of the compression stroke. So, this is very important. So, again while you are writing that the process 3 to 4 is isentropic expansion or power stroke, both valves are closed, we have to know the pressure and temperature at the end of the compression stroke, because while we are trying to quantify the thermodynamic efficiency, we find we are having heat addition. So, we need to know what is the amount of heat being rejected during exhaust blow down, and for that we need to know the pressure and temperature at the end of the power stroke. Fine, all valves are closed. Since this is an isentropic process, there is no heat interaction. So, Q324 will be equal to 0, but W324 will be there, that will be equal to how much? P4 from the PV diagram, that will be equal to W324 is equal to P4 V4 minus P3 V3 divided by 1 minus K, right. So, is equal to, if we use that T4 minus T3 by 1 minus K, that equal to U3 minus U4, that equal to Cv into T3 minus T4. These we will get from the ideal gas relationship, straightforward, fine, no heat interaction, no heat transfer, Q340, W34 we have obtained. So, what will be T4? Because T4 will be equal to T3 into V3 by V4 to the power K minus 1, that equal to T3 into capital V3 by capital V to the power K minus 1. Similarly, P4 is equal to P3 into V3 by V4 to the power K is equal to P3 into V3 by V4 to the power K. So, this is what is the pressure and temperature at the end of the power stroke. We have seen that P2 and P3 are the, if we go back to my previous slide where in our PV and TS diagram, T3 is the maximum Tmax and P2, P3 are the Pmax from the PV diagram, and we obtain, and from TS diagram we obtain that T3 is the Tmax. Of course, because T3 is the state at the end of the combustion, so temperature will go high, definitely, no problem. Then we will discuss about process 4 to 5, that is exhaust blow down, or we can, this is exhaust blow down, or this is constant pressure heat rejection, right. In this process, of course, intake valve is closed, intake valve is closed, exhaust valve is open, intake is closed but exhaust is open, we have to have open exhaust valve, otherwise how we have blow down. So in this process, constant volume process, there should not be no, so W 425 will be equal to 0, Q 425, that is very important, that is Q out, that will be equal to M into CV into T5 minus T4, right, this is very important. So T5 is as good as T1, so mass flow rate of mixture into T1 minus T4 into CV. This we are getting. This is of course Q out, capital Q out, Q45 is equal to Q out is equal to, while specific heat rejection is equal to Q45 equal to Q out will be equal to definitely CV into T5 minus T4, that equal to U5 minus U4, that equal to CV into T1 minus T4, because T5 is as good as T4, fine. So we have obtained the heat transfer, the heat rejection at the during blow down process. We have seen that no work done is because constant volume process. Now finally, this is very important that we have to discuss the this is exhaust blow down, and final process is what, that is the constant pressure exhaust. So this is blow down means constant pressure, constant volume heat rejection. That means we should open exhaust valve whenever piston is slightly away from BDC at the end of the power stroke, and we will record, we need to expel out certain amount of combustion product only to reduce the pressure inside the cylinder. That is what I told many a times. So and we should expel out certain amount of combustion product from the cylinder, and by that time piston will reach at the BDC, so that the volume is remaining almost constant, and this is also a good approximation as a constant volume heat rejection. And next process is process 5 to 6. Process 5 to 6 is the exhaust. This is exhaust process rather and constant pressure. Let us say P naught, constant pressure P naught exhaust. Here what is happening? Exhaust valve is open, intake valve is closed, and while we are having exhaust process, so we will have only constant pressure process, and W 5 to 6 will be equal to P naught into V5 V6 minus V5 equal to P naught into V6 minus V1, because V5 is equal to V1. If we go back to my previous slide where we have drawn the PV and TS diagram, V5 is as good as V1, and this point is 6, so V6 is as good as again V2. This point is 6, so this point is again V2. So we have obtained the, from this analysis, considering air to be an ideal gas and following the ideal gas relationship, we have obtained pressure and temperature at the end of the compression and combustion as well as the power stroke. We have obtained the heat input and heat output, rather heat rejection, heat addition in the combustion process and heat rejection in the exhaust blow down, and we also obtained the work done required during the exhaust and the intake and as well as the combustion process. So we have obtained work done during intake, combustion as well as the exhaust, constant pressure exhaust process. So from there we have to now quantify the thermal efficiency of the diesel cycle, because we have seen, we know the heat input to the system, we know the heat output from the system, that is heat addition, heat rejection, and we know that what is the amount of work is done into the system, because work done is, we have seen that work is done during intake stroke, during combustion process as well as during the exhaust process. So if you try to now calculate thermal efficiency, so thermal efficiency of the diesel cycle, eta diesel eta thermal diesel, that will be equal to, so why? So we have heat input to the system, and what is the net work? So we have what is the net work output, that is we need to know, because per stroke we are getting work, we are supplying work to the engine during intake as well as during the exhaust stroke, and also during intake stroke and during exhaust blowdown, and also during the combustion process. So and we are getting work output from the engine during the power stroke. So we know what is the net work output. So what is the net work output from the engine? W net divided by what is the heat input to the system. So what is the work output from the system and heat input to the system, and that is the thermal efficiency of the diesel engine. So we have seen that during intake stroke we have to supply some amount of energy, and that the engine will borrow from flywheel. During the combustion process again work is done, and we are getting work output from the engine during the power stroke, and also we need to supply some amount of work, we need to supply energy during the constant pressure exhaust. So what is the W net? That equal to Q in minus Q out divided by Q in. So that will be equal to 1 minus Q out by Q in. So heat Q out is the heat rejected from the system, and Q in the heat input to the system. So what is the heat rejected from the system? That is Cv into T1 minus T4. So 1 minus Cv into T1 minus T4. What is the heat input? Heat input only in the combustion process, that is Q2 to 3, that is Cp into T3 minus T2. So this is Cp into T3 minus T2. So that is the heat input. So Cp by Cv, that will get K. So what I can write, that equal to 1 minus T4 minus T1 divided by Cp by Cv, that equal to K into T3 minus T2. And we have to rearrange, because here T4, T1, T3 minus T2, and we will ultimately get efficiency in terms of compression ratio and the cut-off ratio. So cut-off ratio is basically beta, and then compression ratio is, so if I rearrange this term, so eta thermal diesel equal to 1 minus T4 minus T1 divided by K into T3 minus T2, right. Beta is equal to cut-off ratio is equal to V3 by V2, that is what we know. Beta is equal to cut-off ratio, V3 by V2 is equal to T3 by T2 is equal to T3 by T2. Our compression ratio, that is very important, that is V1 by V2. Compression ratio is equal to V1 by V2 RC. So that is equal to RC is equal to V1 by V2 is equal to T1 by T2. So if I rearrange all this term, and then I can write that this efficiency of the diesel cycle can be written 1 minus, if I rearrange this term, we have to do a few more steps, and it can be written that the efficiency of the diesel cycle can be written 1 by RC to the power K minus 1 beta to the power K minus 1 divided by K into beta minus 1. So this is very important. So this is beta to the power K minus 1, and so this is the eta thermal of diesel cycle. This is very important, that eta K is equal to Cp by Cv, K is equal to Cp by Cv, beta is the cut-off ratio, this beta is the cut-off ratio, and this is compression ratio. So, if I rearrange the terms and if we do a few more steps, it can be shown that the efficiency of the diesel cycle can be written 1 minus 1 by RC to the power k minus 1 into beta to the power k minus 1 divided by k into beta minus 1. So, this is the efficiency of the diesel cycle. So, from this, that it is the value in the value of the terms in the bracket is greater than 1 when this equation is compared. I mean, so if we compare the efficiency of the, this is the efficiency of the diesel cycle, and if we compare this with the efficiency of a thermal efficiency of Otto cycle, then what can I write? So, thermal efficiency of the Otto cycle, that is we have derived in the last lectures, and that we have obtained 1 minus 1 upon RC to the power k minus 1. So, this is the thermal efficiency of the Otto cycle, right. So, thermal efficiency of the diesel cycle and thermal efficiency of the Otto cycle we have written. Efficiency of the Otto cycle we have derived in my last lecture. Today I have derived the thermal efficiency of the diesel cycle, and we need to do a few more steps only to arrive at the final expression, where I have written the the definition of beta, RC and K. So, what is seen if I compare these two efficiencies, diesel and efficiency, that the extra term that is there in the efficiency of the diesel cycle, that is within the bracket, bracket, and this is greater than 1. That, so when this equation is compared with the Otto cycle, that for a given compression ratio, thermal efficiency of the Otto cycle will be greater than the thermal efficiency of the diesel cycle. So, for a given value of compression ratio, this value, the quantity within the bracket, because beta cutoff ratio k is always greater than 1, beta is always greater than 1. So, now because V3 by V2, if I see the PV diagram, V3 by V2 is greater than 1. So, beta is greater than 1, k is always greater than 1. So, the term within the bracket is always greater than 1. So, if I compare the efficiency of diesel cycle and Otto cycle, so it is what is seen that for a given compression ratio, efficiency of the Otto cycle will be always higher than the diesel cycle. So, efficiency of the, so for a given compression ratio, for a given this term is always greater than 1. So, for a given RC or compression ratio, thermal efficiency of Otto cycle is always greater than thermal efficiency of diesel cycle for a given compression ratio, right, because this quantity is always greater than 1. If that is the case, I mean, then it can be concluded that constant volume combustion at TDC is more efficient than constant pressure combustion. So, what I can conclude, if we compare the efficiencies of diesel cycle and Otto cycle, since the quantities within the bracket is always greater than 1, since beta is always greater than 1, k is always greater than 1, then for a given compression ratio, it can be shown that the efficiency of the Otto cycle is always greater than the efficiency of the diesel cycle. So, that means the constant volume combustion at TDC is more efficient than the constant pressure combustion, right. But since the diesel cycle, the CI engines are having higher compression ratio, always are having higher compression ratio, CI engine operate with a higher compression ratio than SI engine. So, of course, efficiency of the CI engine will be always higher. So, for a given compression ratio, it can be shown that the efficiency of the diesel cycle will be less than the Otto cycle. That means the constant volume combustion at TDC is more efficient than the constant pressure combustion. But question is, CI engines are having normally higher compression ratio. The CI engine operates with a higher compression ratio, and that is why efficiency of the diesel cycle will be always higher than the Otto cycle. So, with this I stop here today, and I will continue our discussion in the next lecture. Thank you very much.